Think for a moment about what separates the inside from the outside of a black hole. You probably picture something. A surface, a barrier. A point where space ends and something else begins. A wall. There isn't. It's a mathematical surface. A calculated boundary. That's not comforting. And that's what makes a black hole one of the most unsettling objects in the universe. The event horizon, the boundary between inside and outside, isn't made of matter. It doesn't emit radiation. It's got no thickness, no temperature, nothing you could detect upon crossing it. And yet, on the other side of it, 5 of the fundamental laws of physics stop working. Not just what a black hole is, but where, specifically, and why, our most advanced physics begins to break down and where it collapses entirely. In 1916, a German physicist named Karl Schwarzschild was serving on the front lines during World War I when he solved one of the most difficult mathematical problems in theoretical physics. Einstein had published general relativity a year earlier, in 1915, with a system of equations describing how matter curves, space and time. No one had found an exact solution for those equations yet. Schwarzschild, in the trenches, found it. His solution described space-time around a sphere with all its mass squeezed to a single point, and it revealed something extraordinary. There's a critical radius around any mass. Compress that mass down to this radius or smaller and the geometry of space-time shifts irreversibly. This became known as the Schwarzschild radius. For Earth, this radius is about 9 millimeters. The entire planet, with its 6 billion trillion tons, compressed to the size of a marble. For the Sun, it's 3 kilometers. For M87, the supermassive black hole at the center of the Messier 87 galaxy, the event horizon is larger than the entire solar system. With 6,500 million solar masses, its shadow is larger than Pluto's orbit. Schwarzschild didn't live to see the impact of his work. He died of an illness a few months after sending the calculations to Einstein. And for decades, most physicists believed black holes were mathematical curiosities. Interesting solutions to the equations, but objects that probably didn't exist in nature. John Wheeler, in 1967, was the one who popularized the term black hole and gave these objects a name the public imagination could hold on to. Here's what makes it so unsettling. There's nothing physical at the event horizon. No wall, nothing detectable. So why is crossing the horizon the most extreme transition any object can make in the universe? The answer begins with what happens to light. First, forget what you think you know about why light gets trapped. The immediate intuition is gravity just pulls it in. Wrong, and the difference between these two explanations changes everything. Escape velocity is the concept that connects everything that will happen from here on out. To break free from any object's gravity, you need a minimum velocity. That's roughly 11.2 kilometers per second from Earth's surface. Launch it slower? Gravity pulls it back. Faster? It escapes. Distance doesn't matter as much as initial speed. What matters is enough kinetic energy to overcome the gravitational well. Now, apply that concept to an extremely compressed object. Pack more mass into less volume, and surface gravity shoots up. So does escape velocity. At exactly one point, the Schwarzschild radius escape velocity reaches c, the speed of light. This isn't a metaphor. It's not an approximation. At the event horizon, escape velocity literally equals the speed of light. And the consequence is direct and relentless. Nothing moving slower than c can escape. Nothing in the universe moves faster than c. So, nothing escapes. Not matter, not signals, not information, not light. But light isn't only affected at the horizon. It begins to feel the distorted geometry long before that, in a region called the photon sphere, which sits at roughly 1.5 times the Schwarzschild radius outside the event horizon, still in the theoretically escapable region. At this distance, the curvature of spacetime is so pronounced that light can orbit the black hole in circles, photons traveling in a straight line. Because a straight line in curved spacetime is a curved trajectory from our point of view, can complete a full orbit around the black hole before escaping or falling in. This is the first break from Newtonian physics. Newton described gravity as a force acting on objects with mass. Light has no mass. According to Newtonian physics, gravity shouldn't affect it. Einstein's general relativity says that gravity isn't a force. It's a curvature in the geometry of spacetime. and light, as it travels through curved spacetime, follows the straightest possible path within that distorted geometry. Near a black hole, this straightest possible path curves dramatically inward. It was exactly this geometry that the Event Horizon Telescope captured. The image of M87, released in 2019, was built by 8 observatories distributed across the globe, operating as a single Earth-sized telescope. The image of Sagittarius A, the supermassive black hole at the center of the Milky Way, followed in 2022. What appears in these images isn't the black hole itself, because a black hole doesn't emit light. What you see is the space around it. The shadow in the center is the region where photons were captured or deflected beyond the point of no return. The glowing ring around it is light from accreted matter, distorted and bent along extraordinary trajectories by the geometry of spacetime. Some photons orbiting the black hole before reaching the telescope. These images are the first direct empirical confirmation of the Event Horizon's geometry. Not a simulation, not indirect inference. Real light bent by real geometry. The bright ring of M87 matches the predictions of general relativity perfectly for a 6,500,000,000 solar mass black hole. The shadow size, the asymmetrical brightness from the rotating accretion disk, the photon ring structure, all confirmed. Newton couldn't have predicted any of this. We needed a theory that treats gravity as geometry, and that's exactly what we see. But if light cannot escape, what does a distant observer actually see when something falls toward a black hole? And this brings us to an even more extreme scenario. The answer to this question is one of the most baffling predictions of general relativity. Completely verified by theory and unparalleled in any other physics. Clocks in stronger gravity tick slower. That's gravitational time dilation. A direct prediction of Einstein's equations confirmed by experiments since the 1960s. GPS systems have to account for it, or they'd be off by kilometers and days. It's real, measurable, and verified in labs. Atomic clocks at different altitudes prove it. On Earth's surface, it's minuscule, but real. Near a neutron star, it's dramatic. Near a black hole's event horizon, it becomes absolute. As an object approaches the horizon, time dilation shoots toward infinity from a distance. The object's clock ticks slower and slower compared to the distant observers. This means that, to anyone watching from afar, an object falling toward the event horizon never actually gets there, literally. This isn't an optical illusion or a mathematical trick. The distant observer sees the object slow down progressively as it approaches the horizon. The light redshifts, its wavelength stretches. The object gets redder, then dimmer, then shifts to infrared, then microwaves, then radio waves. Every photo captures it slower, fainter. The last image shows it practically at a standstill, frozen, slowly fading until it vanishes beyond any instrument's detection. Never crossing, never arriving. The conclusion defies intuition. From the outside, throughout the entire history of the universe, no object has ever crossed the event horizon. All the matter that's ever fallen in, still frozen infinitely above it. This is physically correct within the external observer's frame of reference. But it's only half the story, because the falling object experiences something entirely different. Here's the remarkable asymmetry. The photons this object sends outward become increasingly redshifted, spaced out, and weakened. But the object still receives light from the outside universe. From the falling object's perspective, it doesn't see the outside time freeze. It sees the outside universe accelerate, compressed into its own temporal perspective. The closer it gets to the horizon, the more the outside universe is sped up. It's a bidirectional time distortion. To those watching from the outside, the object freezes. To the one falling, the outside speeds up. Both effects are mathematically consistent with the same geometry. Shift the angle. You are no longer the distant observer. You are the one falling. For a supermassive black hole like M87, with 6,500,000,000 solar masses, the gravitational gradient at the event horizon is surprisingly gentle. Tidal forces, which arise from differences in gravitational pull across different parts of a body, are negligible at this scale. The event horizon of such a massive black hole is so vast that the difference in gravitational acceleration between your head and your feet as you cross it is imperceptible. You cross. You feel nothing special. No alarms, no extraordinary sensations, no barrier. Remember, there's no wall. The region you're crossing is physically empty. The stars around you are still visible, progressively distorted by the geometry, but still there. From the distant observer's view, you never arrived. From yours, you crossed smoothly. Both descriptions are physically valid within their frames of reference. Neither is an illusion. And they're mutually incompatible. This is black hole complementarity, a principle developed by physicists Leonard Susskind and Gerard 't Hooft. Two observers have completely different accounts of the same event, both correct within the physics that each can verify, and neither can compare notes. Because you can't send any information out past the horizon. Any signal you try to send gets trapped right along with you. For stellar mass black holes, just a few solar masses, it's different. The event horizon is much smaller, so the gravitational gradient is extremely intense. Tidal forces stretch any object along the radial direction and compress it laterally in a process physicists unironically call spaghettification. An astronaut approaching a stellar black hole gets torn apart by tidal forces before even crossing the horizon. But for any observer who survives the crossing, once inside the horizon, space-time's geometry has changed in a way unparalleled by anything outside a black hole. And the most important implication isn't that you're trapped, it's that place and direction have lost their meaning. The physics you use to navigate normal space simply doesn't apply in the same way anymore. But what exactly changes? And why does this change make the singularity not just inevitable, but inevitable in the exact same way the future is inevitable? Consider what this means for the physics of the interior. Outside the event horizon, you can move in any spatial direction. Up, down, sideways. You move forward in time, but cannot go back. Space and time have distinct and well-defined roles. Inside the horizon, this distinction vanishes in a very specific way. And this is where physics makes its strangest claim about black holes, a claim that transforms what it means to be trapped into something far deeper than gravity. The spatial direction toward the singularity turns into a temporal direction. And turns here isn't a metaphor. It's what general relativity describes geometrically. Inside the horizon, space and time coordinates swap roles. The variable that described radial distance to the singularity starts behaving like time. The singularity isn't a place in space, it's a moment in your future. The consequence is that moving toward the singularity isn't inevitable, like gravity is inevitable, where at least in principle a rocket could resist. It's inevitable in the same way time moves forward. It's structural. There's no engine capable of pulling you away from the singularity, because moving away would be equivalent to traveling into the past. Penrose diagrams make this geometry visually explicit. They represent the entire space-time where light ray trajectories appear on 45-degree diagonals, which preserves the causal structure and shows which regions can influence which others. In a Penrose diagram of a black hole, the singularity appears as a horizontal line in the future, not in space. Every possible causal trajectory, including those of light rays, which are the fastest allowed by physics, ends at this line. Every possible trajectory converges on the singularity. No maneuver, no force, no angle of approach changes this fate once you've crossed the horizon. Your future light cone, the region of space-time that can, in principle, be reached from your position points entirely toward the singularity. Even standing still is impossible. Inside the horizon, standing still in space isn't a physical option. Any stationary position would require a speed greater than light. The only available movement is temporal movement, and that points exclusively to the singularity. You can't go forward, backward, or sideways. You can only move forward in time. And moving forward in time, inside the horizon, means getting closer to the singularity. How much time you have depends on the black hole's mass. For M87, you could survive for hours after crossing the horizon before space-time forces you into the singularity. For a stellar mass black hole, it's milliseconds. But in either case, arrival is unavoidable. It's inscribed in the geometry. And what you find there makes every previous breakdown in physics seem small. This leaves the question that no theory can fully answer. What exists at the singularity? But why is this question so different from any other in physics? Why can't we simply apply our most advanced equations and calculate what happens there? General relativity answers the first part with ruthless precision. Infinite density, infinite space-time curvature, zero volume. And it's exactly this answer that reveals the problem. When Einstein's equations are applied to the central point of the black hole, to the singularity, they produce infinities. Not just very large numbers we can approximate, actual mathematical infinities, literal results of the equations. In physics, when your theory produces an infinity as the result of a physical calculation, that's not an answer. It's a red flag. It's the theory signaling it's been applied beyond its domain. It's not that the singularity has infinite density. It's that general relativity simply isn't capable of describing what happens there. The theory has reached its limit. This has happened before. Pre-quantum classical physics produced infinities when applied to certain problems of electromagnetic radiation, what became known as the ultraviolet catastrophe. Classical theory predicted that a heated body should emit infinite energy at the highest frequencies. Quantum mechanics resolved this absurdity by revealing that classical physics doesn't apply at subatomic scales. A deeper theory was needed. The black hole singularity puts general relativity in the exact same position. There's a scale where quantum effects on gravity become impossible to ignore. The Planck length, 1.616 x 1035 meters. To give you an idea of how small that is, a proton is roughly 1020 times larger. Below this scale, quantum fluctuations of spacetime itself become dominant, and every classical gravitational equation completely breaks down. Quantum mechanics also has something to say about the singularity. Heisenberg's uncertainty principle states it's impossible to simultaneously know both the exact position and momentum of a particle. A particle with zero volume would have a perfectly defined position, which violates the uncertainty principle. Matter compressed to infinite density is fundamentally incompatible with quantum mechanics. The singularity predicted by general relativity can't be real. In 1965, Roger Penrose mathematically demonstrated that, given reasonable conditions regarding matter's distribution, singularities are inevitable within general relativity. It's not an artifact in special edge cases, it's a structural consequence of the theory. With enough matter, a singularity must form. Penrose won the Nobel Prize in Physics in 2020 for this discovery. Penrose also proposed the cosmic censorship hypothesis. Singularities are always hidden behind event horizons. Nature organizes itself so that the points where equations completely fail are never visible from the outside. It's as if the universe is protecting physics from its own inadequacies, hiding breakdowns behind insurmountable boundaries. But Hawking showed something does get out of black holes. And this placed quantum mechanics and general relativity in direct contradiction to pillars of physics that had never come into conflict before. This is where physics runs into its deepest contradiction, not at the singularity, but at the horizon itself. In 1974, Stephen Hawking combined quantum mechanics with the geometry of the event horizon and derived something no one expected. Black holes emit radiation. The mechanism is quantum in nature. The quantum vacuum isn't empty, it's constantly seething with pairs of virtual particles that pop into existence and annihilate each other before having any measurable effect. Near the event horizon, a pair can be separated before annihilation, so one particle falls in while the other escapes into space. The escaping particle steals energy from the black hole's gravitational field. The black hole loses mass. Slowly, immensely slowly for large black holes, it evaporates. For a typical stellar mass black hole, the evaporation time via Hawking radiation is on the order of 1067 years. The current age of the universe is roughly 1010 years. But in principle, given enough time, the black hole completely disappears. And that's exactly where the deadlock arises, the kind of problem that's kept theoretical physicists awake at night for 50 years. Because when the black hole disappears, what happens to all the information that fell into it? Quantum mechanics has a central axiom called unitarity. Information is never destroyed. Look at the experiments: quantum interference, particle entanglement, the coherence of Bose-Einstein condensates. In all these phenomena, information about the initial state is preserved, theoretically reconstructible by the wave function's evolution. These aren't special cases. They're real manifestations of a principle quantum mechanics structurally demands. The complete physical state of a system at any past moment can be calculated, in principle, from its present state. Every configuration of particles, every position, every spin amount, every interaction, everything is preserved in the fabric of quantum evolution. Information isn't erased. It's not a philosophical preference. It's a mathematical requirement for quantum theory to be internally consistent. If unitarity fails, quantum mechanics' entire probability structure collapses. Probabilities won't add up to 100%. The whole theory loses its foundation. General relativity, on the other hand, allows information to vanish inside the black hole and remain eternally inaccessible. And when the black hole evaporates, it simply ceases to exist in the observable universe. This directly violates unitarity. Two axioms, two theories, one universe. Both statements can't be true at the same time. And neither has backed down in more than 50 years since Hawking published his derivation. In 2012, 4 physicists, Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully, known by the acronym AMPS, pushed this paradox even further with what became known as the firewall paradox. They showed that preserving information as unitarity demands would have a direct physical consequence at the event horizon. Instead of a calm, imperceptible boundary, the horizon would be a wall of high-energy radiation that destroys anything trying to cross it. This directly contradicts what we discussed earlier. For a supermassive black hole, crossing the horizon is imperceptible. Black hole complementarity and the firewall paradox are incompatible. Both derive from solid physical principles. Both can't be simultaneously true, and no physicist yet knows which principle gives way or how. The information paradox is considered by much of theoretical physics to be the most important open problem in fundamental physics. The true implication of this paradox goes far beyond a simple theoretical dispute. The problem isn't that one theory is right and the other is wrong. The problem is that there are regions in the universe where the two domains overlap, where gravity is so extreme that its quantum effects can't be ignored. A black hole's singularity is the most extreme example. The Big Bang is another. In these regions, our two best theories come into direct contradiction. And that means both are approximations of something deeper we haven't discovered yet. This is why we need a theory of quantum gravity. Not as an academic refinement, as a fundamental necessity for physics to keep working. This theory needs to make predictions about what happens at scales smaller than the Planck length, about spacetime's structure at extreme densities, and about what happens to information when spacetime's geometry becomes radically non-classical. It's the biggest open problem in fundamental physics. Two approaches dominate current attempts. String theory solves the problem by replacing point particles with vibrating one-dimensional objects. Strings and predicts extra dimensions beyond the 4 we observe. Loop quantum gravity quantizes spacetime itself, making it discrete at the Planck scale instead of continuous as general relativity assumes. Both make predictions about what would replace the singularity. Both suggest, in different ways, that it isn't real, that some physical structure would replace it once gravity's quantum effects are correctly modeled. What exactly replaces the singularity remains unknown. A successful theory of quantum gravity would also need to explain what happens to information. It must demonstrate that Hawking radiation preserves information in ways current physics can't track, or modify a black hole's spacetime causal structure in some way that dissolves the firewall paradox. Solving the black hole information paradox would be the most significant achievement in physics since general relativity in 1915. No exaggeration. That's the assessment of serious theoretical physicists. Black holes are the only place extreme enough to force these contradictions into their clearest form. The natural laboratory the universe created to test the very limits of physics. So what is the black hole really telling us? In 1783, John Michel calculated that a sufficiently dense mass could have an escape velocity greater than light and called these objects dark stars. It was intuition without the full mathematical apparatus. In 1915, Einstein published General Relativity. In 1916, Schwarzschild derived the exact solution from the trenches. In 1965, Roger Penrose proved that singularities are inevitable. In 1967, John Wheeler coined the name black hole. In 1974, Hawking showed that they evaporate. In 2012, the firewall paradox revealed that the contradiction between quantum mechanics and gravity is encoded in the structure of the event horizon itself. In 2019, the Event Horizon Telescope produced the first direct image of a black hole. In 2022, the second Sagittarius A, at the center of our own galaxy. Every step in this timeline expanded the scope of the problem. What began as a mathematical curiosity in the trenches of World War I revealed itself to be the object where the most precise physics humanity has ever produced stops working. The black hole isn't just an astronomical object, it's proof. Proof that we're in the middle of a revolution in physics, that the theories we built in the 20th century, however precise and powerful, are approximations of something deeper we can't yet see. The most important physics of the 21st century probably starts exactly here, where general relativity waves the white flag and quantum mechanics refuses to accept its answer. If you want to be around when that answer finally comes, subscribe to the channel. This is what the black hole is telling us. Physics hasn't failed, but we aren't done yet.